welcome everybody. Welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Sinan Du, and I will be your main host tonight. So it is wonderful to see all of you here in person, and we also welcome our online audience of a comparable size who's watching the live stream. As some of you may already know, we try to feature unique and special topics in these public lectures, especially those that you would like to hear about. And tonight, it's another very popular topic as suggested by our audience feedback, black holes. So tonight, specifically, we will be learning about how stellar mass black holes, those formed from dead massive stars, can affect their cosmic environment. Before we get started, I would like to give a very big shout out to the entire team who is supporting our event behind the scenes. So those of you may have already met the front desk staff. We have our tech team here, and also Jay, who is managing the live stream for us. And since this is a hybrid lecture, we also have online chat moderators to answer all the online questions on YouTube. There are subject matter experts on this topic, and I will also let them to quickly introduce themselves. So first we have Andrew.
Hi, everyone. My name is Andrew Sullivan. I'm a second-year graduate student here at Stanford, and I do research on neutron stars and black holes. I hail from New York City originally, so I see there are some New Yorkers in the virtual chats. So hello, I just came from there today. And I'm super excited to answer any questions that arise about Katherine's talk.
Thank you very much, Andrew. Next, we have Chloe.
Hi, I'm Chloe. I'm also a second-year grad student at KIPAC, and I work on supermassive black holes, kind of understanding what's going on in those systems at the center of galaxies. And yeah, I'm super excited for tonight, and I look forward to answering any questions that come up on the online chat.
Fantastic. And last but not least, we have Jack.
Hi, everyone. I'm afraid I'm not able to turn on my video at the moment, but I'm Jack Dinsmore. I'm another second-year grad student in KIPAC, and I study pulsars, which are quickly spinning neutron stars. And I'm from Boston, so I see there's another Bostonian in the chat, so it's great to have you all here.
Well, thank you all. For those of you who are joining us online, you can see the chat box on the right-hand side of the window. We welcome all kinds of questions there and also encourage you to engage in discussions. So for all of you who are joining us today in person, we will have your questions saved until the very end during the Q&A. And of course, Katherine will also be here even after this lecture ends to chat with you if you would like. So it is my greatest pleasure to actually introduce tonight's speaker, Professor Katherine Blundell, who actually just flew in yesterday from the UK for tonight's talk. She is currently visiting also another distinguished professor here at KIPAC, Professor Roger Blanford, who is also studying extreme phenomena in the universe. Katherine Blundell is a professor of astrophysics at the University of Oxford. Her research interest is very broad, but mainly focused on the extreme events and phenomena in the universe, including supermassive black holes, quasars, and also massive stars, and also plasma physics. Katherine actually launched the Global Jet Watch project to advance research on relativistic jets from stellar mass black holes in the universe. She has been awarded many prestigious medals and also awards, not only for her research, but also for her services to the field of astronomy and education of young people. So tonight we will be listening more about the black holes and microquasars that can evolve actually on human-friendly timescale. So without further ado, let's welcome Katherine.
Perfect when technology works. Good evening, everybody, and thank you, Vinay, for your very kind words of welcome. It's an absolute pleasure to visit Stanford University again, not just to be working with Roger Blanford on topics that we're very interested in, but a real treat to meet so many people again and to have such interesting conversations as began at the KIPAC tea earlier this morning. Well, I guess I should begin with a bit of an apology for anyone who's feeling a little bit hypnotized by the movie that's on my front slide. I'll be explaining what that's all about and its connection with black holes a little later on in my talk. But I want to begin by making the following remarks. Black holes are for real. Black holes are out there. Black holes are part of science fact and not merely science fiction. They were predicted by mathematics long before they were discovered. The whole concept came from pure thought, from someone who was very free to think. And at this precise moment, I'm not talking about Einstein. The initial concepts of black holes predated Einstein by well over a century. The earliest thinking on this came from the Reverend John Mitchell in 1783, which was quite an epochal year, being the year when there was the formal end to the War of Independence, the Revolutionary War. So it was an epochal war. It was an epochal year. The war ended and the field of black hole studies began. So what exactly is a black hole? A black hole is a region of space that is so dense, matter is so compact, that gravity is so strong that nothing, not even light, can escape. And as I mentioned, the first thinking on this came from the Reverend John Mitchell. He was a vicar in North Yorkshire, which is in the north of England. It rains a lot, so it's not like Stanford, there's no beach, no blue skies. And so he would think about life, the universe, and everything. And he conjectured that if stars became so extremely massive, maybe they might have a bit of a dragging effect on the light that left the stars. Maybe this would be a more manifest, a stronger effect if the star was more massive. So he published this work, as I said, in 1783, and he was thinking of something which perhaps now we would call a dark star, a star where the gravity is so strong, light can't escape. This was the earliest thinking on black holes. It was followed by Laplace and Einstein, and of course, many others. But the key point is, gravity is so strong, nothing, not even light, can escape. So let's start thinking about escaping from near a black hole, near but not too close. Let's think about what's known in the jargon as escape velocity. Escape velocity is how fast you have to travel if you want to escape from a massive body. And I realize not everyone in this audience may love equations as much as everyone else, but please try to love this one. Ignore the number 2, it's just a number. Ignore the letter G, that's just a label for a number. They don't change, they're not doing anything. M signifies the mass of whatever body it is we're talking about. And so it's intuitively straightforward. The larger the mass, maybe the more rapidly we have to flee if we are to escape it. Now let's imagine that the mass is condensed into a smaller volume. Let's say that volume has a characteristic size or radius denoted by the letter R. The smaller that is, the closer we are to the mass, the faster our escape velocity has to be if we are to succeed in escaping. So far, so good. Don't you just have to travel faster and faster if you want to escape from some mass m, perhaps the mass of a black hole? Well, not so fast, literally. It turns out that you can't travel infinitely fast in our universe. There is a speed limit. You cannot travel faster than a quantity we denote by the letter c, which stands for the speed of light. Light travels incredibly rapidly, but not infinitely fast. And so the problem is that you cannot travel faster than the speed of light. So if you've got a body of mass m and it's got a size that we're describing by r, then there's a boundary around it, which might be really quite close. That boundary defines the speed, the distance r, where you would have to travel with speed c if you were to escape. That region of space defined by that distance is something we call the event horizon. Within the event horizon, you would have to travel faster than a speed you cannot travel faster than. The event horizon defines a membrane of no escape. If our sun were to collapse into a point-like region of space, then in fact, the escape velocity for, the event horizon for our sun would just be 3 kilometers in extent. So if you were closer to the point mass that the sun would collapse to than 3 kilometers, you'd be trapped there forever. You would never be able to escape. If you were just outside 3 kilometers, then if you could travel at the speed of light, then yeah, you'd be able to escape. Approximately unscathed, a little bit stretched, but approximately you would be able to escape. So whereabouts might we find black holes? It turns out that these days we think that there are black holes at the centers of almost all galaxies, certainly including our own galaxy, the Milky Way. So just to orient you, we think that there's a rather large, rather massive black hole right at the center of our galaxy. We also think there are millions, hundreds of millions of galaxies distributed throughout the disk that you see just there. So just to orient you, we are over there on the left. And the journey time between Stanford and the galactic center is about 26,000 years if we could travel at this very, very rapid speed that is the fastest speed that we can travel at in our universe. Well, how can we learn anything about this black hole? The usual answer to how can we learn anything about a black hole is by the effect that they have on their surroundings. So let me show you some time-lapse images here, the very center of our galaxy, taken at infrared wavelengths, wavelengths of light that can penetrate through all the dust that gathers in the deep potential well at the center of our galaxy. And I hope you can get a sense of stars moving on little orbits around that yellow cross that's right at the center of that image. So there are time-lapse images, sequences of images that show changes with time of how stars are orbiting around something that you couldn't actually see if there wasn't a yellow cross there. We believe that to be the location of a black hole. This is from Reinhard Genzel's group in Germany, and this one is from Andrea Gayes' group in UCLA. So this one's in color, hooray. We can see the paths of the stellar orbits. And if you know the type of stars that you're dealing with, and therefore you know the masses of those stars, you can solve for the orbital dynamics, and you can work out what must be the mass of the unseen body that all these stars are orbiting around at the very center of our galaxy. And it turns out that the mass that you end up deducing the presence of on the basis of the effect of the star is a mass of about 4 million times the mass of our sun. So that's a pretty hefty black hole. It's actually relatively mild in comparison to the supermassive black holes that Chloe spoke of a few moments ago. But I want to talk about other black holes, less massive black holes than the one right in the middle of our galaxy. I want to just consider how it is that black holes can do anything exotic and unexpected on the mass, on the material that they encounter that's nearby. How can they do anything at all, given that black holes suck? Don't black holes just suck in everything without trace, given that gravity is always attractive? Well, the key point is that gravity isn't the only law of physics at play. And indeed, the richness of the phenomena that we as astrophysicists and physicists study in the universe is that we're trying to decouple how it is that all the laws of physics act in concert with one another. It's the combination of the laws of physics that gives rise to the exotic and rich phenomena that it is such a delight to study. So let me show you what happens now when we have a black hole in orbit around a star, much like our sun. So the black hole is at the very center of the red disk that's orbiting there. This red disk, by the way, is a holding pattern of matter that's being gradually and slowly sucked towards it, obeying the law of conservation of angular momentum. In other words, if something is rotating and swirling, it will carry on doing that, all the more so as it gets sucked closer and closer and closer to the center. What's happening here is that the gravity of the black hole at the center is pillaging the matter of the normal star, colored here in white. It's attracted into this holding pattern, much like the path of the planes that often seem to take rather a long time to land over London Heathrow. That red disk of matter is known as an accretion disk. Matter is accreted towards the black hole. A significant fraction of that matter is swallowed by the black hole, increasing its mass, increasing its angular momentum. But black holes are very messy eaters. They're greedy, but they're messy eaters. And it turns out, and this is somewhat indicated by the blue stuff somewhat arising from this red disk, matter is spun out and spat out of the material that's being sucked and dragged in towards the black hole. So how do we begin to study them and to see what's going on? It's pretty crucial here that we don't just take a monochromatic single approach to studying the behavior and the phenomena of black holes. We make use of a whole spectrum of radiation. And I don't just mean the whole spectrum of optical light to which our human eyes are sensitive. I mean the rest of the electromagnetic spectrum, the long wavelength radio waves, we'll see those in a moment, all the way up to the very high energy light that we can detect from material near black holes in X-rays and in gamma rays. It's important to appreciate that by studying at all these different wave bands, we're probing different physics, all of which is relevant to building up a whole picture of how the universe works. So when we look in optical light, pretty much we're looking at where fusion is taking place in the universe. And it may be that in the sort of middle of the left half of that screen, you recognize the constellation of Orion, a bunch of different stars that is quite famous in the northern winter sky. The bright light at the top of that is the moon. And before you say, well, the moon isn't undergoing fusion, let me remind you that the moon's light comes from reflected sunlight, and the sun, our nearest star, is most assuredly undergoing fusion. So a lot of optical light, not all of it, arises from fusion. Some of it comes from thermal, a measure of the temperature of material. More of that a little later on. When we study at radio wavelengths, we're studying the presence of magnetic fields and relativistic particles in the universe. And that's very enriching to study as well. And of course, when we study X-rays, we're learning about where gravity is most strongly active in the universe. It's important to emphasize that embracing all these different wavebands and all the techniques that go with making use of those is crucial for building up a full picture. So let me show you the optical view of a very, very famous supermassive black hole system known as Cygnus A. This is an optical view. Most of what you see there are individual stars within our own galaxy. If I zoom into the center, you see the fuzzy blob, which itself is a combination, a conglomeration of lots of other stars. A great big galaxy in an ellipsoidal shape. We call it elliptical, but deep down they're 3D. We think they're ellipsoidal. And right at the center of that galaxy is a black hole whose mass is the best part of 1 billion times the mass of our sun. So this is what it looks like at optical wavelengths. But if you observe this exact same region of sky at radio wavelengths, you see a very different picture. From one length to the other, the extent is over 100,000 light years. So traveling at a very, very fast speed of light for 100,000 years, you would span the distance of one end to the other. Right in the middle there is a black hole 1 billion times the mass of our sun, as I said. And what you may sense is that emanating from the vicinity of that black hole are oppositely directed jets, which shock on the intergalactic medium that they're expanding into and accelerate particles, which inflate these radio-emitting balloons, regions of space that combine magnetic fields and relativistic, highly energetic particles. Now, this is not a unique, a one-off in our universe. There are these kind of jetted quasars, supermassive black holes from which oppositely directed jets emanate all across the universe. And I've spent many happy times studying these. But a big question that I don't know the answer to, and that the astrophysics community across the world doesn't know the answer to, but is an area of active and vibrant research, is how do you launch jets like this, oppositely directed jet, from the vicinity of a black hole? It's a really important question because objects like this have a massive influence way beyond the event horizon that surrounds their black hole. How does it all happen? Well, objects like this evolve on timescales of 1 million years, or 10 million years, or 100 million years. And those are not human-friendly timescales. And so it seemed to me expedient to turn to such systems as these, but those that would evolve on much more rapid timescales, much more appropriate for human attention spans. So let's come back to our galaxy now and focus on that region of our galaxy that I've put 2 red rings around. This is an optical image just from a digital camera on a tripod, I have to say. If we look at the very center of those 2 rings at radio wavelengths, you guessed it, we see a different picture. We see this amazing balloon of radio emitting plasma. It's over 2 degrees in extent. But I want to focus on the very bit in the middle where there is a microquasar, a scaled down version of the big jetted quasars that I showed you a couple of slides ago. How do we begin to zoom in and see what's going on and understand the jet activity a little bit more? Answer, you get hold of a big worldwide telescope. We use the NRAO's, the National Radio Astronomy Observatory's very long baseline array, affectionately known as the VLBA, to study the object right at the center of that radio image that I showed in my previous slide. And again, we use the technique of time-lapse imaging a whole sequence of images which over time show you changing behavior. So this is the galactic microquasar, zooming in on angular scales that are really tiny. What do I mean by very tiny? I mean less than 1,000th of 1 degree, really tiny. What happens when we do a time lapse of these? Well, we see that blobs of plasma are ejected in opposite directions, but that axis, the line along which they are ejected, seems to change with time. So these images were taken every day for about 40 days. And we discovered all sorts of good things by studying these. And this was super, but other people wanted to use that radio telescope as well for their science. So this started the process of thinking, well, how can we understand this more deeply? Let me now zoom into that central object on a slightly different angular scale. This is now probably about, this is 10 seconds or so, much smaller fraction, a much larger fraction of 1 degree, but still very much sub-degree. And just to give you a sense of scale, this is what we're looking at here. I made this image using the Very Large Array, which is in New Mexico, again, operated by the National Radio Astronomy Observatory. So this is rather cool. This image that we're looking at, the one at the top, encapsulates a zigzag curly corkscrew snapshot. It's just a single image, it's not a time-lapse image, of what this object looks like at a particular instant in time. I wonder if you can spot a resemblance with that movie that I was hypnotizing you with at the start of my talk. Just imagine if I could have hijacked the Very Large Array radio telescope in New Mexico every day for 163 days, and if I could color code the material moving towards us blue and the material moving away from us red, and if the material was squirting out the jets at speeds of about 1/4 of the speed of light. The reason why you've got that zigzag curly corkscrew pattern is because the speed at which the jet plasma is launched is about 1/4 of the speed of light. And that's plenty to see some quite significant and interesting relativistic effects. What's actually happening is that the axis along which that jet plasma is launched traces out a precession cone every 6 months or so, something like that, 163 days. And at any instant, oppositely directed pairs of plasma ejections are squirted out into the interstellar medium. Some people find it a little easier to take in the concept that I'm talking about here in terms of these pairs of packets of plasma ejected about an axis, an instantaneous axis, but collectively over time. It traces out a cone. Think of the action of a paddle of a kayakist in the rest frame of the kayak. That's the action that this black hole is demonstrating, is causing on the material, the accretion disk that's responsible for the launch of the jet. It's extraordinary. All this activity, by the way, is completely outside of the event horizon of the black hole. But the influence that black holes have outside of their event horizons is extraordinary and dramatic, as we'll see. But there are a couple of problems with what I've just said. One of them is that I can't use any of these radio telescopes day in, day out, because other people want to use them for their science. But the other problem is that I can't get any radio telescope anywhere in the world to color code the speed at which the plasma is moving, or even color code it according to whether it's moving towards Earth or away from Earth. So radio images are beautiful and enriching and scientifically informative, but they actually don't tell us about the underlying dynamics that we're trying to elucidate. So it's time to switch to another waveband. And I'm now going to switch back to the optical waveband. Not to take images, but to use a technique called spectroscopy, which splits up the light into all of its colours, a whole gamut of different colours or different wavelengths across the optical spectrum. So we're very familiar with how sunlight is dispersed into a rainbow by raindrops in a cloud. We know that, and it's beautiful. What I'm going to talk about is the technique by which we disperse starlight into its full rainbow. Not, of course, by raindrops, they're really unreliable, even in my country, but with an optical element inside an instrument called a spectrograph. But more than that, we're going to employ the technique of time-lapse spectroscopy, repeated observations using a spectrograph that mean we can elucidate the underlying dynamics. If you're not familiar with the word spectrograph, just hear it as speedometer. When we're doing time-lapse spectroscopy, you can think of the fact that we're using a spectrograph as an accelerometer. Spectroscopy means we can study dynamics, and that's where things get really exciting. So let's do spectroscopy on the constellation of Orion, the one I mentioned earlier. You may recognize some of these stars, Betelgeuse and Bellatrix being the top ones, and then there's Orion's belt and his sword further down. So if we disperse the light from each of those stars into a rainbow, into a spectrum, then we see how the light is dispersed into its own little rainbow. I could go through all of the stars and show you all of their spectra, and they're pretty interesting, but I want to draw your attention to the spectrum of this object that's called Messier 42, and just zoom in on that. And I hope you can see the spectrum of this object has little peaks, which actually arise from light from lots of oxygen atoms that are present and lots of hydrogen atoms that are present. The technique of spectroscopy means that we can fingerprint the present specific chemical elements. We can scan the periodic table and say, what's present? What chemical elements are present? Where have they come from? Which star has been ripped apart to give us the chemical elements that we're observing? But it gets better. We don't just do chemistry with a spectrograph. As I said, we do dynamics. And that comes about by an effect very well known to physicists called the Doppler effect, which is the business whereby something that is moving towards us appears bluer in color. The wavelengths of its light are shorter than the wavelengths that they would be if we were in the rest frame of that object. Light material that's moving away from us appears redder. The light from it appears redder in color. It has longer wavelengths. So this is what I mean about using a spectrograph as the speedometer. So this is the technique, time-lapse spectroscopy. Okay, that's the technique sorted out, but how do you get hold of telescopes that you can dedicate to a particular field of study? The answer to that question is you think about the time sampling that you want to have. Round the clock is a really good way to go. This is what motivated me to set up the network of telescopes that Zenan referred to earlier, the Global Jet Watch. It's called global because it is. There is a global distribution of telescopes. They are distributed in longitude so that there is always one of them in darkness. So if you can imagine you want to study a target in the top left corner of this image where the galaxy is, different telescopes in different parts of the world can take it in turns to be in darkness. Cloud is a bit of a showstopper, I have to say. So I set up these telescopes. How do you build a network of telescopes? Quite hard work, lots of concrete, lots of broken fingernails, but lots of persistence. And then here we go. So this is my telescope in Chile, where I'll be headed at the weekend. This is the top end. This is the bottom end of my telescope in India. I know it's the one in it, they're all identical pretty much. I know it's the one in India because see these sort of little grills over the primary mirror fans? Those are squirrel-proof grills. It is a bad case of no fun to be chasing squirrels around a circular observatory. Take it from me. So at the back end of the telescope, there are various different cameras. Sorry, let's just go back to that. Right at the top, there's an imaging camera and a filter wheel, and there's another little telescope there for different purposes. But the thing on the left connects to an optical fiber, which comes out of the little green box and goes all the way down to this big shiny red box, which is a spectrograph, inside of which we have an optical element which disperses the light into the spectra that we're after. This is the dispersing element, and it's really, really precious, the way that it just disperses the light so we can see what's going on and understand the dynamics. Here's one of the telescopes. Here are some of our commensal cameras to give us supporting photometry. It's handy to know when a particular target is getting brighter, it's going to flare. We can then use the spectroscopy to understand what exactly is going on. But this is the network of telescopes, and they're all delivering fantastic time-lapse spectroscopy. I'll present a couple of results to you in a few minutes' time, but I first want to tell you about an important spin-off of the Global Jet Watch, an important spin-off of our investigations of black holes. So let me talk about some of these spin-offs. The telescopes are hosted in residential schools. Now, please don't think posh British boarding schools that certain British prime ministers attend. Not that sort of residential school at all. Here is the school in South Africa, and here is a particular group of girls outside the observatory just at twilight, while we're waiting for the sky to get dark before observing one night. The paradigm is that before local bedtime, the students are free to play with the telescope. And I deliberately use the verb to play because that's a very freeing verb to use. If you start telling people about the learning outcomes that are expected of them, it's a bit of a pressure. If you tell people to play and to explore the night sky, well, most people are pretty relaxed about having a go and having a play. There is, I have to say, quite a lot of giggling that takes place. But when teenagers are having fun, they're in a place where they can learn. And the key point is that they learn how to use the telescope for themselves. This again is South Africa. This is India. And believe me, they really do wear pink shower kameez to observe at night. It is extraordinary to bring to these girls the gift of science, the experience of science, the sense of technology being something that they can be in control of. It has quite a profound effect on these students, but they're the ones in the control seat. This particular, this is from my India observatory, where I was a couple of weeks ago. I have never experienced the thirst for knowledge that I have as I experience time after time when I visit that school in India. Over half of the students at this school are first-generation literates, so parents didn't get a chance to learn to read or write or go to school. The school was founded by the government of India so that the bright children of rural families could receive a formal education. And as I say, their thirst for knowledge is absolutely unparalleled. Their minds are like sponges, and many of them, as a consequence, do go off and study physics or engineering, or physics and engineering at college. And that's pretty special. If ever there was an epoch in human history when it was time to engage and raise up the next generation of globally astute, scientifically literate young people, I reckon it's about now. Let me show you a couple of girls. These were the first two girls from the South Africa school who ever observed. I'm in the tiny little corner, the top, in my study in our home in Oxford. It's Jenna sitting down there controlling the telescope, Katie standing up. Any of you who've ever done astronomy, you know that at the start of night, you're a little bit tense and a little bit anxious. Is the sky going to stay clear, or are clouds going to rock up? And then the first time, they moved the telescope for themselves. And then this was when they'd imaged their first galaxy. It's extremely important to me that the schools are not merely spectators, but that they gain skills. Katie, in that last slide I showed you, Jenna went off to study physics and astronomy at University in South Africa. Katie went off to do nuclear physics. These are Magisha and Lorraine, also from South Africa. Let me share with you an email that I got from one of the Indian students who subsequently went to read physics and engineering. Dear Madam, hope you saw the image of Jupiter. That's a planet, by the way. It was magnificent. I don't teach spelling, I teach how to play the telescope. We even saw, and this is a list of different targets. You'll notice M42 there, Messier 42. Guess what, madam? Every night in my dream, I play only with stars and nebulae. Once I enter the observatory, I forget everything. I feel I have entered heaven. Has a profound effect on them. And so that's an important spin from doing a research program, which of necessity needs to have a round the world distribution of telescopes, but in so doing, engages, I believe, youngsters in those developing countries into science. But it's not that easy working in developing countries. This encapsulates one of the main problems that I've been facing. Sometimes there is no power, no electricity, can't operate a telescope without power. In India, the local electricity was camera-fryingly bad. I had so much expensive gear destroyed by the spiky electricity in that part of the world. So at one point I decided I couldn't stand it anymore. I managed to raise the money to build a solar farm. So this is the observatory at the Indian school. It's on top of the school roof above the academic block, and the solar farm is on the right there. I'll tell you a little bit about this, and then we'll get back to what we've learned from these telescopes about an aspect of the black hole microquasars behavior, SS433. This is the horse that delivered the steel with which we built this shed to store the batteries that store the chemical energy collected by the solar farm. These are my Australian colleagues with whom I do the Global Jet Watch. This is the telescope on the school roof with frames that support the photovoltaic panels. It was very hot, hard work building the solar farm, but it is fantastically reliable. And these youngsters now know that once you've installed your infrastructure, thereafter you get energy for free out of the sky. We've done the same thing in South Africa because load shedding was so very tricky to deal with. But from this setup, we get time-lapse spectroscopy for all sorts of different science projects, the principal one being this microquasar SS433, which exhibits all sorts of dynamical behavior. I won't go into this now in view of the time, but just to say the different spectra do change with time. And it turns out there's quite a clever technique you can do that we figured out a few years ago, which is that if you take the sum of the simultaneously measured blue shifted light and the red shifted light, turns out you can derive with a perfectly straightforward calculation the velocity launch vector of the plasma ejected from the vicinity of the black hole. We've got loads of spectra now. loads and loads. And this is not even 10% of what we've got. But let me show you an edited highlight. There are 4 different spectra here from Australia right, Australia left, Chile, and just going off the top, South Africa. Using this little calculation, you can predict from every single spectrum the launch speed and the launch angle of the plasma that was launched from the vicinity of the black hole, just outside the event horizon of the black hole. And you can make a prediction about what it should look like on the sky. So you're regaining what we would have loved to have been able to get from radio telescopes if we could color code the direction of the material, whether it was moving to or from Earth, the speed at which it was moving and all that sort of thing. So that red and blue dotted panel is a prediction from the time-lapse spectroscopy. How do we know whether we're doing things right? You test it against observations. So using the ALMA radio telescope in northern Chile, we made a radio image and confronted our prediction with what the radio data said. Jackpot, we've got it right. So we're able to use the technique of time-lapse spectroscopy to really determine the underlying details of the jet launch and put this together with other measurements of different spectral features that sadly I don't have time to go into. We don't just study black holes, we study all sorts of things that influence their surroundings. A particular favourite is stars that explode, and I've learned to really love nova explosions. Partly, I mean, originally I thought a nova explosion was just something you practice on until the galactic supernova comes along. We haven't had one of those since before the British invaded North America. I'm sure they're not causally related, but novae are really interesting in their own right. They launch jets, and so studying those jets informs us on black hole jets as well. So I must finish now, but the Global Jet Watch is about studying the science of an ever-changing sky with spectrographs. And if you'd like to learn more about the transforming science that we're doing and how we're transforming young minds, then please take a look at this website. But I think I should now finish. Thank you.
Well, thank you very much, Katherine, for a brilliant talk and also maybe a little bit of the spin-off of all the cool objects that you have studied. Would you like to come to the stage? So we are going to do our Q&A. For any in-person questions, I am going to repeat so our Zoom audience can also hear. Over there.
Thank you so much for the brilliant talk. It's so inspiring. You are truly changing the world.
You are too kind.
I have a couple of questions. First one is, in your research on jet launch, do you see any evidence of interaction of dark matter with black holes?
Nothing.
Oh, let me actually repeat that. So in your research, you actually see any interactions between dark matter and black holes?
I see no evidence for any interaction with dark that I would attribute to dark matter at all, but plenty of very interesting behaviour, even without invoking dark matter.
And would you mind saving the next one for later when chatting with Katherine? Thank you. And we actually have an online question from Maggie asking, how do we actually know the laws of physics apply when it comes to black holes? Or do we just assume it?
That is such a good question, Maggie. We don't know that. We presume that. That's our starting point. And actually, when behaviour in extreme environments such as black hole deviates from what we expect, that's when we're learning something new about the laws of physics in environments that are different from those that we can test here on Earth.
Absolutely. We got to start from something. Yes, question here.
Hi, amazing talks. So The question I have is, do we see any jets originating from Sagittarius?
Question was, do we see any jets originating from the Sagittarius A star, which is the location of the supermassive black hole of our own galaxy?
That is a really good question. So just in the KIPAC tea that we all enjoyed this morning, we were shown an image in gamma rays of plane of our galaxy, and either side of Sag A star, above and below, were big bubbles measured by the Fermi satellite in gamma rays. Now, these are big bubbles. There are reasons why. I won't trouble you with those reasons right now, but there are reasons why we don't think those are the jets themselves, but we very much think there are good reasons for thinking they were populated by, filled by the jets. So I think probably the most conservative thing I think I could say is that there have been jets coming from Sagittarius star in the past. I don't know of any direct evidence for jets right now, but certainly there have been in the past.
Great. Oh, over there.
Following up on that, why wouldn't we see jets? Wouldn't we expect to see jets coming off the black hole?
I like the way you think. Many of us are very expectant that jets should be associated with black holes. But it turns out that if you think of all the black hole population, the population of black holes, the supermassive black holes at the centers of galaxies, less than 10% of those right now would be observed to possess jets. There is certainly a duty cycle associated with jet activity in with these big black holes. That's something that appears to be a characteristic of ever so many of the stellar mass black holes, the lightweight black holes in the disk of our galaxy. So whether or not you're going to get jets, I mean, you know, goodness, I personally wouldn't have predicted jets from first principle. I don't think any of us would have predicted jets from first principle, but they seem to be very prevalent in the universe. But you do need certain conditions to be right. You need fuel, you need angular momentum, and all sorts of other things probably. So it's not necessarily worrisome that we don't see black hole jets from all black holes all of the time.
Great, we'll come back to you in a second. Another question from online audience Legend, asking, do black holes have magnetic fields?
We think so. We think so. They don't inevitably have black holes. Black holes don't inevitably have magnetic fields. We think they may well, either they themselves would have magnetic fields threaded, or remember that accretion disk I was talking about, the holding pattern material? Might be that is what's threaded. It's threading the magnetic field.
Thank you. And there's a question over there.
Yes, thank you very much. So, I personally work in science. People care a lot about them. My wife is a surgeon. How can we get you, in my opinion, this is going on human health. How can we get people to, I was particularly moved by the end part of your lecture, not just about women, but about giving knowledge around health. How do we get anybody to really care? I mean,
Thank you very much for that question. And I would say, on a personal note, you know, caring about what is happening in the universe is actually a very tiny fraction, and maybe a very tiny fraction of you would think, you know, what's happening out there is more important than our everyday life. But I appreciate the note and the question. was how do we actually get people to care more about what's happening out there, and perhaps also, you know, getting people engaged to contribute to collective knowledge, like what you did with the global jet launch.
So I think exposing people to the narrative of what we're investigating and what we're studying is really important. If people don't have a clue what's out there, their thirst for knowledge begins to increase. But I think I would like to dispute your point that what's going on out there is more important than what's going on this planet. I think everything is important. I think finance is pretty important. I think economics is important, and I really think human health is important. But what is common to all of these things that you just referred to is you need quantitative skills to do all of these well. I happen to believe it's a life skill to be able to read a graph. And so I think actually embracing all of these things together is beneficial for each of them separately and collectively. But I think if people don't ever hear the wonders about space, then there's no way that their interest can ever grow.
Thank you for that very brilliant answer. And actually, on a similar note, Eric Levine online was asking, what are the methods that you actually use to analyze your data? So you were showing those 4 graphs of 4 different spectrum taken at different times, and all together you put them together as a time-lapse spectroscopy. So what kind of method do you use, if you wouldn't mind elaborate?
So there are a number of different steps involved in the processing of our data that go from when the photons land on the silicon of the detector to hurtling around the planet, to land on the data servers in Oxford, to serving them up into meaningful scientific quantitative data that you can do science with. One of the first things we do is to calibrate the wavelength dispersion of each and every spectrum. So subtle changes in temperature make a big difference, so we calibrate carefully. Seismic activity, which is a bit of a problem in Chile, I have to say, rattles the optics, and so we do have to calibrate all that stuff carefully. But what that means is that in a given part of the spectrum that the light that we've dispersed, we can absolutely say with certainty that particular peak of light has a wavelength of 6563 angstroms, or whatever the number is. So that means we can determine with certainty, has that light been emitted by hydrogen atoms, or by oxygen atoms, or nitrogen atoms, or iron atoms. A lot of steps go into it. There are a number of these that are already automated. There are a number that are automatable, but there are a lot of steps that just rely on communing with the data, playing with it, tossing it around in your mind, thinking, what's going on? What could be going on? Using our human imagination is a big part of studying the data.
Yeah, and it was all worth it when you actually see all your optical data align perfectly with the radio one, right?
It was a special moment.
Okay, one more question. Over there at the back.
Yeah, is there a theoretical limit to how heavy a black hole can get, and also how light it can?
The question was, are there theoretical limits on the black hole mass, especially the kind that we were studying?
So I'm not aware of any upper limit to the size of the black hole in any sort of specific sense. I mean, the pathways that lead to the growth of the black hole might give you a sort of a limit. A trite answer to your question would be, the mass of the universe. But quite so facetious. But the time taken, the universe is only 14 billion years old. So if you want to start thinking about what are the growth pathways for a black hole getting bigger, then there has only been a finite amount of time, depending on when you thought that black hole was first seeded. Is there a minimum size of black hole? I mean, I don't think there's a theoretical minimum for the mass of a black hole, but there are reasons we have certain expectations of what minimum masses would be, again, based on growth pathways that we observe.
Thank you, Katherine. Initially, I wanted to stop just there, but one more online question from Rainbow, a 9-year-old, asking how can I just become an
How can I become an astronomer?
Yes. What would you recommend?
I would say learn to love maths. I would say learn to love physics. I would say learn to love reading books. Learn to love using your imagination. All of those things. How would you answer that?
Wow, throwing right back at me. Well, I would just say definitely reading books. I got into astronomy in high school after reading one of Hawking's books, illustrated version, even without understanding the illustrations. But it got me very intrigued, and that's how I started my journey. So I would definitely agree with you on reading books. Awesome. Well, let's thank Katherine again. Before we wrap up, I would also like to thank everybody and give a little bit of plug of what's coming up next. So we will going to have a pretty full schedule for the spring. Coming up next is a STEM festival on the Stanford campus. It's on Saturday, April the 20th, and there will be multiple stations, booths featuring live demonstrations, hands-on activities, and also lab tours. This event is especially family and kids friendly, but adults, you can find everything there. And then the following Saturday, we are going to have Noches Astronomicas, which is an event in Spanish for high school students and college students, where we would be talking about the solar eclipse, the moon, the sun, and also having a panel Q&A on college education and STEM careers. And finally, in May, we are going to have our next, the second part of our black hole two-part series. And this one, instead of being the stellar mass black hole, as Katherine was talking about in this lecture, will be featuring supermassive black holes. And it will be given by one of our amazing research scientists, Dan Wilkins, who is also just in the audience. Sorry for calling you on that. But yeah, Dan will be giving that lecture in May. And if you would like to follow us and get a notification of any upcoming events we are going to host or participate, we welcome you to either follow us on social media or just sign up for our mailing list. So yeah, thank you everyone for joining us tonight. Let's bring everyone back to the screen. Hope you had a great time here, and feel free to talk to Katherine more. And let's also thank our chat moderators over there. Thank you, everyone.